Hello everyone. In this video, I will show you how to use custom script to record locations of a trace, such as the locations of the proteins on this piece of DNA. The traditional way we do this is to produce a trace on this DNA molecule by clicking that, and we can locate the peaks by either record position at where the mouse position is, or use the record position of a section, which records the location of the peaks above a section of your choice, and also record position at designated locations such as the highest point. Now in the latest image metrics, I added a new option called custom recording. So you can load your own script using your own algorithm to find the peaks. And I will introduce you a new algorithm using local maxima to locate peaks automatically. So I'll first show you how to load the profile. Then I will show you how the technical background behind the new profile. So first, let's go ahead to load a profile. The script, I put it under the scripts folder. So let's go to the sources. It's under scripts. It's called find peaks. So after the script is loaded, you can find it under the right click menu. And here you have this new profile called find peaks. Okay, let's see first what it does. Okay, let's click that. It should automatically find all the proteins peaks along the trace. So it does the job nicely. So identified 4 peaks. So as you see, it does not require any more user interactions. Just one click of the profile, it helps automatically find the peaks. Now let's take a look at what's the algorithm behind the new profile. But before we do that, let's first take a look at how it's done traditionally in image metrics to find the peaks. Now, here I show you an example of a protein which has 3 domains, and I would like to trace the protein. Now, traditionally in image metrics, we use a method called section. So what it does, so after you produce a trace, so here it shows you this trace, which basically passes through the protein masks. And traditionally in image metrics, it's done through the use of a section, which is this red dashed line. And the issue with using section is first, the choice of the section, it takes a bit of trial and error. So for instance, in this case, with the section I choose, it identifies 1, 2, 3, 4, 5 peaks, which is not ideal. In this protein, we probably only want 3 peaks because it has 3 domains. So this is not ideal. So if we lower the section threshold, the level of the section a little bit, it should give us like 1, 2, 3, 4 peaks. At least it can avoid this peak. So it takes a bit of trial and error. You have to precisely locate your section line in order to find the peaks that you want. And another issue with using the second method is that neighboring peaks, they are counted. But in reality, they should be grouped as one. For example, in these 2 peaks, they are essentially on the same piece of protein domain. So they should be grouped as one. There's no need for 2 of these. But in the section method, there's no way to undo that. It always picks all the peaks, even though they're neighboring each other. And the third issue with this is that unwanted peaks of low prominence could be identified, such as this peak here in the green box. Now I'll talk about what does prominence mean in a sec, but in a nutshell, it basically is if the peak, even though it's tall in absolute height, but relatively speaking, in its neighborhood, it's relatively low. So this is like a low prominence peak, and it shouldn't be identified even though it has the same height as the other two peaks, like this one, that one, but it should not really be a peak on itself, right? It should not be identified. So that's an unwanted peak. And in the section method, sometimes this unwanted peak, you cannot avoid them. In this case, we can avoid them by lowering the section threshold a little bit. But in other cases, it may not be able to avoid them. So that's the three issues with using section method. And it's also not a complete automatic method. So it requires users to interact a lot. So cumbersome, to say the least. Now, what's the new method in my custom script? Okay, it's called the automatic peak finding through local maxima. It uses a built-in MATLAB function called isLocalMax. So what it does is it tries to identify all the local maximum of a curve. So in this case, in our trace, we have like 1, 2, 3, 4. There are 4 local maxima. Okay, there are 4 peaks in this curve. And so apparently we don't want all these peaks. So here we have to introduce a new concept called prominence. So I just mentioned. Prominence is calculated as this formula. So what it does, for example, what's the prominence of this peak here? So to do that, you extend a horizontal line from that peak to both the left side and to the right side until it meets or intersect with another peak or to the end of the graph. So in this case, it reaches the end of the graph to the range, to the axis limit. And so when you find that intersect, okay, which is the endpoints of this of the axis limit, right, between the intersection points, right, between the peak and the intersection point, you have a valley, and you identify the lowest valley. In this case, which is this one, which has a depth of 8. And on the right side, this is the biggest valley, right? It has a depth of 13. The prominence is calculated as the minimum of these two valleys, right? The smaller valley, which is 8. That's how we define prominence. And we can do the same thing for this peak. It has a prominence of 2 because the depth, right, on the right side is smaller than the depth on the left side. And they can do the same thing for this peak, which is 3, and so on for this with is 1. So once we calculate prominence, we can then filter them, right? So peaks with low prominence can be excluded if we specify a target prominence value such as 3. So in this case, if I use a prominence of 3 and any peak that has a smaller prominence than 3 are excluded, which means that this peak P2 and this peak P equals 1, they are excluded. So if we specify a prominence of 3, only these 2 peaks that stars in red are chosen. So the peaks with lower prominence are excluded. So that's one benefit of using this algorithm. And the other one is you can specify minimum separation between peaks. So in this case, you can see that the separation between this peak and the first and second peak is 0.65, and from the second to the third, and from the third to the fourth is both 0.45. So if we specify minimum separation at 0.5, that means the peak 2, peak 3, and peak 4, because they're too close to each other, they will be grouped as one, and you only using its most prominent one. So only the fourth peak is chosen. The nearby peak are grouped into one. So that's the second advantage. So you can specify minimum separation. So this process is, for my testing, is very good. And the process can be completely automatic without any user interaction. So you can specify a minimum prominence and optionally a minimum separation, then you can easily identify the peaks of your target. So let's compare the old method and the new method. In the old method with a section, we can easily chosen, for instance, here 5 peaks, which a lot of them are unwanted, right? And it's not automatic, takes time, trial and errors. But in the new method, you only need one click, right? Pick the method. You already specify your threshold value for prominence and the separation. You just click the profile, it automatically identifies the peaks for you. So here it identifies 3 peaks perfectly. As you can see that this unwanted peak is not included in the new method, most likely because it does not meet the prominence threshold. And the neighboring peaks, as you can see, only one of them is chosen, right? Because of the separation threshold. Now I'm going to make some demos of the new algorithm, but before I go there, let's take a look at what the code on the Lighthood does, right? So I have the code open here. So that's the code. That's my profile called find peaks. And for the end users, you only need to take care of the user input section. And in reality, the only parameter you need to take care of is the minimum prominence. Okay, it basically specifies the height of the peak. I mean, the localized height of the peak. Okay, I think that's a way to say that. And if you want to know more about what prominence, how it's calculated, you can read MATLAB's documentation on its local max. That's the function that's used in this algorithm. And there are 2 other parameters here, which is the max number of peaks. You choose sorted by their prominence and the minimum separation, which I just talked about. So these are less important, but the most important part is the minimum prominence. So that's the only parameter you need to take care of. And once you figure that out, right, you use that to determine how tall your feature is that you want to identify as peaks. That's the only thing you want. And then the rest, the code take care of itself. So that's the code underlines it. Now let's go back to do a few more demos of this new algorithm and see how well it does. So let's turn to some protein demos. Let's go to an image and pick some proteins. Let's go say particle 7. Okay, so here we have a protein like a dumbbell shape. There's 2 domains here. And so here you have like these, okay? And apparently the trace here is not very good. It extends a little bit to the background. And this can cause issues to the algorithm because it has a dip here, and which can make the endpoint the peak more likely. And I would not like that. So in reality, if I chose record find peaks, it will find 3 peaks. So the endpoint is identified as a peak, right? And that's because most likely it's because the dip here in the middle, right? That's because of the noise, and also the endpoint really far extends outside the protein, right? If the protein is not masked well, so I would love to pick a better mask, and there's several ways to do that. And first, let's see the mask more clearly so you can see what it does here, right? So that's the mask. Let's turn down the transparency, okay? So this is like, I want to unmask this area because that extends to the background. I click unmask this area. You can also find it under the mask submenu. Unmask this area, it's the same thing. So once you unmask this area, you trace this again. So let's do this again. Let's clear the mask markers. And now you can see you have a curve without any of the noise that we saw just a moment ago. So now you can use the algorithm. And now you can see it identify the 2 peaks nicely. So for the algorithm to work well, you need to mask the particles well as well. So that is something to keep in mind. So always make sure that your masks are um, appropriate. So let's try another particle. Let's see, let's go to particle 28. Now here we have, let's see if we can turn down the mask a little bit. Turn off the transparency, turn down the transparency. Okay, so now we go. Here's we have a 3-domain protein, like a triangular shape. So let's click this. And as you can see, the trace, it does not pass through the middle domain. So first let's talk something about this protein. So this is a protein that has it's a dimer. Okay, it has 2 so the dumbbell, I mean the bars on the 2 arms here is C-terminus, okay, and the of each monomer, right? The N-terminus dimerized in the middle. So that's the structure of this protein. So here the trace, it does not go to the middle protein. So what can we do in this case? So because if it doesn't trace well, it won't matter, right? It could not. There's no peak in the middle, right? So you have to make sure that the trace goes through the middle. So what can we do about that? So to do that, you should add a middle point in the middle protein. So what you do is you double click the middle domain. So here I double click, it basically adds a middle point in your trace. Okay, it forces the trace to go through the middle right, in the midway. So double click the middle domain. Now to produce a additional anchor point in the middle. Now remember the trace, it goes with a direction, the 1, 2, 3. So it goes start at 1 and then passes to the 2, the midpoint, and then it ends at 3. And it follows the same direction in the trace. The 1 starts on the left. The middle is where the color intersects here at point 2 here. And the color matches the trace on the image as well, and ends in 3. The 3 endpoint is on the right side. So now you have like at least a peak in the middle, right? So that's how you trace this protein properly. So now we have that. Let's do our algorithm. Let's pick the find peaks profile. See how it does. So it does a pretty good job, you see. It identified the 3 peaks nicely. And notably that the 2 peaks in the middle, it only picked 1 of them. And that's where the minimum separation comes into force, right? Even though these two peaks in the middle, they are symmetrical, they have the same prominence, most likely. Yeah, they have the same prominence. But because they have the minimum separation set in our parameter in our profile, so because they're too close to each other, now only one peak is chosen. So that's very useful because they're essentially one floating domain, right? There are no two peaks, they're just one peaks. So only pick one of them. All right, let's take a final example. Let's see. $18. All right, 18. So this is a protein with a long linker arm. And let's see this more closely here. You see, so this is essentially the same protein as the one that we just saw. Only in this case, the arm length is asymmetric, right? So the arm here from the middle to the bottom domain, right? This is shorter than the arms from the top domain to the middle domain, right? So this is a symmetrical length of its arms. Now, let's see how it does. Let's record, find the peaks. Yeah, it does a pretty nice job. So yeah, that's all for today's video, and I show you how to use custom profiles to record your locations. Useful, for example, in our example, find the peaks. Now we can write your own custom script and load it to do whatever you want. You can also customize my script to better locate the peaks of your target. Right? You can also do other things. So that's all for today's video. Thanks for watching.